Today we are going to discuss concavity and the importance of the second derivative. Now, so let's real quickly kind of talk about how the derivatives work for us. We know if we're given f of x, this is our function. In other words, in particle motion, we would call that like our position graph. If we take the first derivative of our function, we get the slope. And we talk about this too. If we find the slope of position, we're going to get velocity. And if we take the second derivative, we're going to get what's called concavity. Now, concavity is going to be kind of like our change in velocity, which is our acceleration. Now, how does this make the graph look? Well, of course, the function would give us any value on that graph. So this would give us the value on our graph, a point. The slope kind of gives us what direction we're going. Is the function increasing? Is the function decreasing? Is the function going up? Is it going down? The concavity, this is going to give us the shape of the graph. In other words, its curvature. In other words, it's telling us why does a parabola bend? Why does it? So it gives us that curvature of the graph. So we're going to spend some time today talking about concavity. So let's start with a function that is differentiable. Again, we don't have to worry about continuity because we know differentiability implies continuity. So if a function, we say a function is concave up if the derivative is increasing. Now, what does this say for us? We are saying that the slope is increasing. In other words, sometimes we call this the slope of the slope. So let's look at a concave function that is concave up, like a happy parabola. At the very bottom, we have our vertex, or the relative minimum. If we look before the vertex, we know that the slope is negative. Sorry about that. I had to pause there for a second. So we know if the function is going down, the slope is negative. Likewise, afterwards, the slope is positive. But now let's talk about what's happening with the second derivative. Well, if we notice, way over here, my slope is negative. But as I move to the right, my slope gets less negative. It's increasing. My slope is increasing. So therefore, what we're saying here is, if a function is concave up, we say that the second derivative is positive. Over here, too, the second derivative is positive. Now let's talk about the vertex. Now at the vertex, we know that the first derivative is 0, but what about the second derivative? Same thing. Well, the second derivative at a vertex is still positive. It's still concave up. Now we're going to use this tomorrow talking about what's called the second derivative test. It's how we use the second derivative to determine if we have max or mins. So if we have a function that is concave down, again at the top, we have our vertex. Beforehand, the slope here is positive, and afterwards the slope is negative. So that's what we call that a relative maximum. You might remember that from the first derivative test. But let's look at the concavity. This says if a function is concave down, if the derivative is decreasing, if the slope is decreasing. That's what this says right here. And if I look way over here at the very left, right, my slope is positive, but as I move to the right, the slope is getting smaller. It's getting more negative. So the slope is decreasing from a very steep slope to 0 slope. That is that tells me that the slope is decreasing. So here that is saying that the slope here is less than 0. Same thing over here, less than 0. At the vertex, just like here, the first derivative is 0, but our second derivative is still less than 0 because it's concave down. So To test for concavity, if a function is differentiable, whose second derivative must exist, for example, a line won't happen, like if I have y equals x, a line will have zero concavity because the second derivative doesn't exist. It's at zero, so we don't worry about that. If the second derivative is positive, we say a function is concave up. If the second derivative is negative, we say a function is concave down. So let's see here. Let's look at an example. We want to determine the functions for which the function is concave up or down. So anytime they talk about concave up or down, we're going to need the second derivative. So let's look at our example right here. Example number 1. This is our second derivative. Oops, sorry, let's do our first derivative first. Sorry about that. We're going to get just x squared minus 1. Our second derivative is 2x. Now, before we go any further, let's think about what this function looks like. This is a cubic graph. Most cubic graphs look like this. Now, this one does have a little bit of a bump in it. We'll see that later on. But if you notice, at this point right here, the function is concave down. At this point over here, we can notice the curvature. This is concave up. So the question that some people always want to know is, well, what's happening here at this point? Because there's a point where the function goes from concave down to concave up. We want to know is what's happening at that point where they meet. Something special is. It is a critical number for us, but it is a critical number for the second derivative. But we don't want to call it a critical number because that could be confusing. Remember, critical numbers are ideally just really used for the first derivative. So this point right here, where the function changes from concave down to concave up, is what we call a possible point of inflection. Or a PPOI. So we find these just the same way we would find the critical numbers of the derivative. So we're going to set our second derivative equal to 0, or our second derivative to d and e. If I set the second derivative equal to 0, we just get 0. There's no place where it does not exist, just like before. And then I'm going to do my sign test again. In doing our sign test, my only possible point of inflection is 0. Now notice I'm using my second derivative. Over the past few days we've been using our first derivative. And our second derivative is just 2x. And we want to find out what does that do to our function. Okay? So remember, this is called a possible point of inflection, or PPOI. And remember, all this is right here is this is where the function changes concavity. Where the function, changes concavity. And we're about to see why we say that. Well, if I pick a number less than 0, so let's pick -1, plug it into my second derivative, I'm going to get a negative. Well, that is telling me this function is concave down. So use your hand, ready? Concave down. Show me what concave down looks like. Don't do that. Concave down. So over here, I know the function is concave down. So I draw something concave down. If I pick something like x equals +1, well, 2 times 1 is a positive. So this is concave up. So I show concave. Have that concavity right there. And now I'm ready to answer my questions. This function is concave up on the domain 0 to infinity. And the reason? Because the second derivative is positive. This function is concave down on the domain -infinity to 0, and that is because our second derivative is less than 0. This hasn't changed anything right there. It's just the same as our answers from before with the first derivative test. Now, the only difference is now we have a special point. This point right here. Do you see how the concavity actually changes? Right here, at x equals 0, there is an actual, what we call a point of inflection. So we can say at, there is a point of inflection at x equals 0, and that is because all you need to write is this, because the second derivative changes signs, and that's all you need to write. So there's a point of inflection right there. So that's where the concavity changes. And you might have heard about that recently with the COVID thing. They're always looking for that change in concavity. When they say they're talking about flattening a curve, if we look at a graph right here, where I go from concave up to concave down, where that point of inflection is, a scientist can look at it and say, oh, the curve is starting to flatten. So points of inflection are very useful for us in science, math, engineering, everywhere. So we're going to take a look at a few more examples in part 2. Hope to see you then.